Let's do it. It's go time.
Welcome to Go Time, your source for wide-ranging discussions from all around the Go community. Find us on the web at gotime.fm, on the Fediverse at GoTime, at changelog.social, and on X at GoTimeFM. Thanks to our partners at Fly.io, the home of changelog.com. Launch your app as close to your users as possible. Find out how at Fly.io. Okay, here we go.
What's up, Gophers? I'm here with Kyle Carberry, CTO at Coder.com. So, Kyle, I've known Coder as the IDE in the cloud, and over time, you've iterated to become a fully open source cloud development environment, a CDE. How do you explain what Coder is and what it does?
Coder is a platform to provision you a development environment on any cloud infrastructure. That might be in a VM, that might be inside of a container, but Coder is kind of a developer's route to provision infrastructure for them to write software inside of. We started with the IDE, which is kind of like putting VS Code in the browser, which is what most people are certainly familiar with us for. And we kind of funneled that into more of a platform where people provision the infrastructure. And a lot of people do use a web IDE with Coder. A lot of people use a local IDE and just connect in.
Okay, so what are teams coming to you for? Who's coming to you?
What people really come to us for, particularly this problem is really exacerbated if you're a large enterprise, is when you have like 500 engineers that are trying to update like a version of Python. And instead, we allow one engineer to go through that tedious work of updating some scripts or some Docker container. And then you can actually just deploy that in one click to say like 500 engineers and make it really, really simple.
Let's laser focus in on the platform engineer. It is that team's job to provide the best infrastructure, the best platform for their given applications, for their teams. What are some signs or signals for platform engineers to think about when it might be time to consider a cloud development environment like Coder.com?
So as a platform engineer, developers might constantly be opening like IT tickets that their computer isn't working properly. They might constantly want to update dependencies, but that's a big mess. You constantly have to email people across your team to say, hey, Adam, could we update from Java 17 to Java 18? Those are the kinds of problems that people typically have. That's the status quo. You ship people more powerful laptops to improve the build times of your projects. You try to reduce the complexity of your products instead of simply, leveraging better hardware. We believe that the future is leveraging the cloud for a lot of these things. You can get more powerful instances in GCP or AWS that can make the build times faster instantly. You can let one developer create a standardized environment and then distribute it to 1,000 so that when you're updating from Java 17 to 18, it's just a simple pull request. You can co-locate your servers right next to something like S3 or a database that you're using in development so that you get immediate data transfers and it's not slow. Many of our customers, which is a crazy thing to say, but they use absolutely massive monorepos and they get clones that go from like 10 minutes or 20 minutes or an hour to simply like a minute or 30 seconds. It's just a lot simpler when all of your engineers are standardized on one centralized piece of infrastructure and then one person can impact the lives of hundreds of engineers. And with that, we don't believe that everything belongs in the cloud. We think that some workloads are really amazing for it, and some are absolutely terrible. Coder should be a self-serve offering to your engineers. It should not be prescriptive, where you migrate all pieces of software development into the cloud. Only the things that really get a lot better by running them in this cloud-native way do we really promote moving.
Well, it might be time to consider a cloud development environment. And open source is awesome, and Coder is fully open source. You can go to Coder.com, get a demo, or try it right now, or even start a 30-day trial of Coder Enterprise. Once again, Coder.com, that's Coder.com, Coder.com.
My name is Natalie, and I'm here again with Jesus, and we are recording now the second part of our topic of the 10 aha moments that Jesus had when reading the Go code base. And we stopped at 6. And would you like to do a quick recap before we jump into 7?
Yes, great. Well, hello, everybody.
Yes, welcome. It's nice of you to join again. I'm just jumping straight back in, but yeah, that's actually a moment.
That's fine. Let's talk. Let me recap. The last episode we were talking about the some aha moments that come from some explorations in the Go source code that comes from a couple of talks that I did. One was around the different parts of the different building objects like slices, maps, and channels. And the other ones will come from the compiler itself. Another talk that I did around the understanding the Go compiler, and we explore these different aha moments. One of them was how slices work under the hood. That was surprising for me. Another one was about the syntax and how the syntax of Go have a representation inside the compiler that is the abstract syntax tree, and having that knowledge about how the abstract syntax tree is represented was a aha moment for me, because give me the understanding of what can have a file in Go. What are the boundaries of what exists in a Go file and what can't exist?
What are the building blocks?
Exactly. What are the building blocks, and the fact that there's no more building blocks. There's nothing else that I'm not seeing because I haven't read about it. So that was another cool aha moment. Also, another one was around the cooperative nature of the Go routines and how they wake up each other and how they stop themselves and things like that. That was pretty cool also. It was another very interesting thing. Another one was when I was investigating around the compiler, I started seeing this escape analysis concept, the idea of how the compiler decides what goes to the heap and what goes to the stack, and also the inlining, that the compiler decides when to inline or not a function code. How they work together to give you way better usage of the memory, because sometimes the inlining process makes something that before went to the heap, now because the inlining process now goes to the stack, and that is faster. So that was another one. The other one that I also was super cool for me was understanding when in the compiler start the code that is machine dependent, where in the process of compiling your program, your code gets in a state that is machine dependent. This is pretty late in the process. It's one of the passes of the static single assignment representation. And that was really cool, because then you realize that almost a huge percentage of the compiler is architecture agnostic. And that's pretty amazing. The other thing, and that is related to that, is the fact that TinyGo leveraged that idea and leveraged the SSA representation to build the TinyGo compiler. Basically, you use the SSA representation of Go to get that SSA, use the whole compiler machinery already there to generate the SSA. And instead of compile that SSA to a binary for your architecture, it's going to intercept that point, convert that SSA into a LLM intermediate representation, and that LLM intermediate representation, LLVM intermediate representation, yeah. LLM is
low-level virtual machine, not the large language model.
Exactly. The LLVM intermediate representation, and that LLVM intermediate representation converts your that code into your microcontroller specific architecture. So I found that pretty amazing and pretty smart. And that were the 6 aha moments that we explored yesterday. It was yesterday. The previous.
It's okay. It's okay to say what happened behind the scenes. All good. It became a long episode, longer than expected. So we broke that down into 2.
Okay, I think that's it. That was what we were talking yesterday.
All right. I'm ready to jump to number 7.
Okay, the number 7, that comes from, it's kind of the intersection between my talk around understanding the Go compiler and my talk around understanding the Go runtime. That is the next obvious step. Well, actually, the next obvious step on whenever you are exploring these kind of things is stopping. This make no sense to keep going and keep going. But, well, I'm a reckless person, so I still keep investigating and start investigating the runtime. And as part of that, there was some interesting thing that I saw and was kind of surprising. Not necessarily surprising, but it's kind of, if you think about it, makes sense. But I haven't thought about it before, and then when I saw that, I was surprised. And it's the fact that the compiler compiles to binary code in general. So if you have an assignation of a variable, it's going to be compiled into some binary code that is going to do some register change and some memory access and things like that. But not everything ends up being compiled to that binary code per se. Some of the syntax that you see in the Go source code is compiled to calls to the runtime instead of executing some assembly code, some CPU instruction. Is going to delegate that logic to a chunk of code that is going to be always there. That is the runtime. For example, some very common syntax that we use is inserting things in a channel or reading from a channel. That syntax, it's going to end up converting to a instruction in the assembly that is a call function to the runtime module, to the specific function that sends messages to a channel, send data to a channel or receive data from a channel. So that was very cool because it's this, you see how smart is the design there, because you always have this runtime. The runtime is kind of easy to follow code, and converting all that into assembly to represent the concept of a channel in the final assembly probably is going to get your binaries probably more bloated. But not only that, it's kind of simpler to design that. You have a package that is always there, and your syntax can compile to that based on the existence of that package. So that was really cool. And you can easily see that if you use the Go build flags, if you pass the -s in GC flags, you get the assembly generated when you build your program. And you can see in the assembly there all that calls to the runtime package. So it's kind of easy to see that, and it's, for me, is pretty cool.
Why do you think this was done this way? Or what would be another way kind of doing that would be maybe better for another setup?
I think, for example, there is a concept in Rust that is zero-cost abstractions. That is something that you have the syntax there, but the compiler is going to take care of all that, and it's going to generate the final binary for that abstraction without any runtime cost. That is another way of doing that. That is going to put more pressure in the compiler. It's going to take more time into the compiler to compile all that code. So probably that's one of the reasons. If you have a runtime that is always there and is always ready to just be linked to your binary or be embedded in your binary, probably is faster to compile. And also, I think the code is going to be simpler, because at the end of the day, with all these transformation, all these generate this AST that suddenly represents something, an intermediate representation, and that intermediate representation convert that into instructions. All that, it's kind of more heavy lifting than saying, yeah, whenever you see a channel send, just add a call to a function. And it's simpler. I think that's the idea behind that. I don't know for sure, but that's my guess. It's faster for compiling, or I guess it's faster for compiling, and it's simpler from the mental model perspective.
Does it have something to do with a cross-compilation flags that to kind of support that? From your guesstimate, I know it's a cross of too many topics.
Yeah, no, I think it doesn't need to be related to that, because the cross-compiling part, it's going to be, have some relationship, because if you have your runtime already cross-compiled for another architecture, you don't need to recompile that part over and over and over again. So that is cross-compiled one time, and the rest of your code needs to be cross-compiled. That's the one that needs to be cross-compiled. But at the end of the day, the runtime is just a Go package like any other Go package. So at the end of the day, probably the cross-compiling wouldn't be that different, because at the end of the day, what you will do is something like, okay, the send message to a channel, it's going to be a set of instructions that goes together. and that's it. So I wouldn't expect that to be affecting the cross compiling. But again, it's a guess, as you say, it's a guess.
Is there any like recommendation for when writing your code you can have this in mind, or is this too many layers and this is more of like a general bonus there?
Yeah, for me, I think part of this is about whenever you want to know more about how certain things works, you can check out that and say, oh, okay, it's calling the runtime directly. So whenever I append something to a slice, it's just calling the runtime. So there's some things that are happening in the runtime that you can say, okay, if this is the runtime responsibility, I can easily go to the runtime code and understand what is going on, understand what means append to a slice, or what it means to go to add something into a map or send something to a channel. So you can easily explore that based on that. That's the only thing that I see some value there. In general, my talks are completely useless. So they are interesting knowledge. I found that knowledge interesting, but in general, they are useless. There's not much thing that you can apply directly, because it's about how things works. And to be fair, the Go compiler works really well. So you don't need to know how they work. How the compiler and the runtime work. So it's just about being curious and understanding better certain things. And yes, time to time you find that knowledge useful, but in general, it's more about the pleasure of understanding what is going on under the hood.
Yeah, I get that. I guess that one time where suddenly memory is eating in a wild way, nobody understands why, and that one person knows that one very esoteric one. Fun fact, this is where it comes in useful.
Yeah, it's like, I went to a talk from Nicky Tebeka in GopherCon UK that was about brain teasers. He has a book about that also, but about brain teasers, and was like, I was able to guess like 50% of them. Mm-hmm. The other 50%, I got caught, but that easily actually was like, okay, this is not something that I will expect. But there, some of them I was like, okay, I know that it's going to behave weirdly because I know how it works under the hood. But yeah, it's pretty cool. So, but it's not especially useful in general, as I said.
Keep it in the back of their mind, basically, is what you say.
Yeah, exactly. It's
that one time where compilation is being weird.
Yeah. And yeah, exactly. Understanding some small things here and there that can be interesting.
What's up, friends? I'm here with two new friends of mine from Speakeasy, Sagar Bachu, co-founder and CEO, and George Hadar, founding engineer. So for the uninitiated, Speakeasy takes care of the entire SDK workflow to save you and your team significant time, delivering enterprise-grade SDKs to your customers in minutes. You can generate best-in-class SDKs in TypeScript, Python, Go, Java, C#, and even PHP. So, Sagar, what's your excitement level for APIs and this API world we're living in?
I'm super excited about APIs. I think we went to Gen 0 of the API first revolution, and I think we're actually going to a second one now with the tailwinds of the AI ecosystem kind of causing that to be reinvigorated. So yeah, super psyched to be working in this space right now. I think everyone's at a point now where everyone knows about REST APIs and GraphQL APIs and gRPC APIs. And now I think we're actually getting into the second phase of that, which is how do people ship great developer experience in addition to the APIs? And how do we build like truly best-in-class APIs that turn into long-lived infrastructure, right? This is kind of the vision I think that Stripe helped manifest for everyone in the fintech space, which is an API that really sets the bar for developer experience, but also like it's something you can truly rely on, right? It's a true, if you make Stripe a dependency of your company, you can feel confident doing that. And I think that's the part of API development that really excites me.
I agree. That is exciting. So, George, teams who leverage Speakeasy are those who have leaned all the way in on documenting a solid open API spec and mostly want to be hands off of their SDKs. Is that right?
Precisely. So you're coming to us because you want to be hands off from that process. You want to put all of your effort into documenting your API, and then you're trusting and relying on great quality tooling to turn that into code and documentation, which is what we're doing for you. You're not meant to change or edit the code because it will be regenerated the next time you change your open API. So you ultimately put it in our hands. Once you've committed the changes to your open API, it's off to the races, and you get a new release of your SDK. You'll get a pull request to review. You will have the opportunity to look at the contents of the code, but quite often you can let it hum along creating SDKs for you or new releases of your SDK every time you change your API.
Very cool. Well, the thing that got me with Speakeasy that really helped me understand it was that, as George said, it is hands off. You can just focus on documenting your API via the open API spec. And you still have pull requests, you still have visibility. And in fact, they will even hop into pull requests with you to triage any sort of anomalies or issues that come from the SDK generation and improve the back end of Speakeasy to make future releases better for you. I think this is so cool for teams who want to just be hands off of their SDKs and focus on their product, focus on the core documentation around the open API spec, but still have all that awesome visibility. Okay, so the next step is to go to speakeasyapi.dev. You can start off with one free SDK. That's so cool because you can go there right now and try it out completely free. One free SDK. Let them know the changelog sent you. Let them know JS Party sent you. Once again, speakeasyapi.dev.
Okay, let's jump to number 8.
Yeah, this is another one that it has to do with this understanding on the knowledge that is good to have, and sometimes you don't really understand what is going on. And it's about the binary entry point. Whenever you execute a Go binary, whenever you learn Go, the first thing that everybody said is, the entry point of your program is this main function that you define, and then your program start executing there. Of course, that's not true because we have a runtime. So the very first thing that is executed in your binary, it's a function that is dependent on it's an assembly function, a Go assembly function that is dependent on your operating system and your architecture. And then it's a start initializing things. I start setting up a lot of stuff, the memory allocator, the garbage collector, the different CPU flags, security related stuff. A lot of stuff is done before even your main function is called. So that was very interesting because you see the amount of things that are done before your main function is executed, and it's pretty amazing. Also, during that process, one of the things that happens is that your main function, is executed through a Go routine also. It's not the main process, and the Go routines is something that happens after. It's the Go routine. The first Go routine is created and start executing your main function. So your main function is not executed outside any Go routine, and then you spawn Go routines. Your main function is a Go routine, and actually before your main function is executed, there are other Go routines already executing, like the system monitor and things like that. So there is a huge, not huge, but a very interesting process there before your main function is executed. And yeah, I found that pretty cool.
I mean, on the one hand, it's a lot happening, but on the other hand, it's so fast. And it makes me think of that XKCD comic of where it's compiling, right? That they play swords, and it's kind of how it stopped happening in Go, because the same thing happens, but just faster, basically.
Yeah, it goes really fast. It is actually if you start digging into that initialization process, most of them are very small tasks. For example, the memory allocator is just initializing some structs that are there, but it's not heavy lifting there. Then some things like the garbage collector is just setting some flags here and there, and the garbage collector is set up. It's all small things, small set of structs that you define and a small initialization that you do. And then when the program starts running, it start using that thing. So for example, whenever you need memory, it's going to start using the memory allocator. Whenever you need to recollect the garbage collector is going to kick off and all that stuff. So there's a lot of steps. There's a lot of things that happens between when you start your binary and your main function it's called, but they are very small things, very targeted things. So, yeah.
If one want to go about looking into that, how would you do that?
Well,
how did you do this?
Yeah, I will recommend to go and check out my talk. So that will be a kind of a easy path. But if you want to do it by yourself, that is perfectly reasonable. What I did was went to the GDB debugger and find the entry point that in my case was in the src/runtime/rt0 Linux AMD64.s. That is the entry point. That's an assembly code there. And then I start tracing that and going to the different calls that is doing and see what are that calls doing, what are the initializings and all that stuff. So basically I manually trace all that execution. And that was my process. Was relatively hard. It's not super easy because you have some assembly code there that you have to can understand a bit. It's not something that you need to understand a lot of assembly, but you have to understand a bit. And then you just start tracing all these small steps here and there. Then you have the scheduler initialization, but the scheduler initialization includes the memory allocator initialization, the garbage collector initialization. So there's a big chunk that is the scheduler initialization, but it's initializing a lot of stuff inside. So tracing all that took me time, but it's not especially hard. It's more time consuming than hard. That is what I perceived.
All the links will be in the show notes.
Oh yeah. I can share some links there. And actually, if you see, I usually do that in my talks. Whenever I explain these kind of things, I usually have at the bottom right corner of my slides, I have links to the source code. That is kind of homework for the people if they want to go there and check where in the source code is happening, whatever. And yeah, if you go to the slides of my talk and you start looking the different steps, you are going to see that at the bottom right corner, the link to the source file and the specific version of the Go runtime or compiler. And yeah, you can go there and check it. It's interesting. I don't know how many people do that, to be honest, but I put that there.
Yeah, it's fair. It's nice to have sources for sure. References, yeah. Okay, number 9.
Okay, it's kind of related with what we have been talking. It was the memory allocator. I probably that was more my fault than anything else, but I didn't know. I didn't even thought about the concept of the memory allocator inside Go. Whenever you talk about memory management in Go, normally you talk about the garbage collector, but I never thought about the memory allocator, and the memory allocator was an interesting piece of software that I didn't know. And the memory allocator is the responsible of talking with the operating system and reclaim pages and free pages. So it's very interesting part of the how memory is managed in Go. And actually what it does, it organizes the data in a way that it take pages, set of pages, what is called MSPANs, memory spans, and that memory spans have variables of the same size always. So an MSPAN can have 30 pages, but doesn't matter the amount of pages that it has, it always going to store variables of the same size. That means if you have a MSPAN of 8 bytes, all the variables of 8 bytes is going to go there. If you have a MSPAN of 32 bytes, variables of 32 bytes goes there. And there is a set of mspan size that are defined and are the bigger is the span, the bigger is the space between them. For example, you have a 8, 16, 24, 32, and then I think it jumps to 48 or something like that, and then to 60, and then to 96 or something like that. So it's jumping, and there's more and more space between them. I don't remember the exact numbers, but there's more space between them. That is important to know because if, for example, you store a variable that is 30 bytes, for example, it's going to be stored in the mspan of 32. So it's going to take 32 bytes of space, no matter the size of the struct. So every single variable that is between 24 and 32, it's going to be stored in the 32 span, and it's going to take 32 bytes. So that's the idea. That way you have less fragmentation, you have a very efficient way of storing and retrieving that variables. Also, you have an easy way of reclaiming and freeing that pages in memory. So it's an interesting approach. And that's the memory allocator. Apart from that, you have all these mspans. Then you have for each CPU, you have a one mspan, and then you have a centralized version of all the spans of all the CPUs. And then you have a mheap that is managing everything. And the other thing is the biggest mspan is 32 kilobytes, I think. So everything that goes over 32 kilobytes is going to be handled directly from the mheap and is going to get its own memory pages. So really big data chunks are going to be handled independently outside mspans, and is going to use pages directly in memory, and everything under that is going to go in the mspans that is going to handle that in pages of memory. So the memory allocator asks for more pages and free pages from the operating system. So the memory management is done by the memory allocator. The garbage collector decides what is its use and what is not, but the memory itself, the asking for memory and freeing memory from the operating system is done by the memory allocator. And I didn't even know that exists before because I'm a web developer, basically. So my focus has been always in other place.
Yeah, I would like to watch a talk about that. I feel like I need to hear this one more time.
Yeah, I think in the last EuroPython, Diana Svencheko, Diana give a talk.
From Datadog, yeah?
Yeah, from Datadog, give a talk about that, about how knowing how the memory allocator works, they were able to squeeze a lot of performance and reduce the memory usage and the garbage collector pressure and all that stuff. So that is interesting. And actually about knowing how the garbage collector works and knowing how a structured packing works, how changing the order of the fields of a struct can end up giving you a less memory usage for that struct. And if that falls into the right spot between mspans, you can end up saving big amounts of memory, actually. And yeah, probably whenever the recording is there, check out the talk from Diana.
Is there any action item or like recommended practice that somebody can take from this aha moment?
Yeah, I will say that knowing that mspan size and all that stuff, and knowing the structured packing can lead you to save memory. And that is something that I think I would recommend to check it out, especially if you have a huge amount of instances of something. For example, in Datadog, it's obvious that they have a huge amount of events. So they have some structure that is repeating millions and millions of times. So that millions and millions of times, if you save, I don't know, 30 bytes on each structure there, 30 bytes multiplied by millions of times, you are saving memory there, and you are saving back and forth with the operating system, reclaiming pages and all that stuff. So I think is something to check out if you have probably in the order of millions of instances of any object.
Okay. Still trying to think what. Like I have no. It always helps me to kind of link this in my mind to something, and it's still like hanging there. But okay. Moving on to number 10 and the last one.
Yeah, the number 10, it's kind of related. One of the things that I always say, I always have this, when the garbage collector runs, it runs whenever you have this memory threshold, but can run time to time and without the memory threshold, but you can run manually. But when that runs, there can be different places, right? And was kind of interesting when I just realized that there are 3 cases only, 3 specific cases where the garbage collector runs. One is whenever you call GC, whenever you explicitly call the garbage collector to do a cycle. So that is the GC trigger cycle. So it's manual calling the garbage collector, the obvious one in this case. Then you have another one that is related to time. There is a coroutine that is running under the hood every 10 milliseconds in Go that is called the system monitor. And that system monitor checks if the garbage collector hasn't been called for too much time. And if that's the case, it's going to call the garbage collector from there. It's what is a GC trigger time that is based on time. It's the system monitor detects that and send and calls a GC garbage collector. Then you have the one that was more interesting for me, that is the GC trigger heap. That is this one that is related to the Go GC environment variable that defines when the garbage collector have to pass based on the size of the heap in the previous pass. So by default, it's 100%. So what it means is whenever you do a garbage collection pass, you end up with a certain amount of memory. Let's say 16 megabytes, for example. The next pass is going to be whenever you double that. Whenever you reach 32 megabytes of RAM, it's going to trigger a garbage collection phase. And for example, after the garbage collection, you get into 20 megabytes. So the next pass is in 40, that reduces the amount to X. And then whenever you reach 2X, it's going to call again and all that stuff. So that is how the GC Pacer works to do that check of whenever you double the memory. But when that happens exactly in the code, because you are asking for new variables, new structs, and things like that all the time. So when are you checking if I surpass that memory? And it's kind of simpler when you understand that the memory allocator is there. The trigger heap, the garbage collection heap check, is done whenever you ask for a new page of memory. Whenever you need a new page of memory, whenever you request for new memory, new block, new chunk of memory to store variables in any of the MSPANs, you are going to check if that is surpassing the threshold. And then if it's surpassing the threshold, it's going to call the garbage collector. So that is exactly the exact point where it's checking that. So there's these 3 cases is whenever you reclaim a page from the operating system, it's when the garbage collector could run if the threshold is surpassed based on time from the system monitor and whenever you call it manually. So, and that's it. There's no any other place where you are calling the garbage collector.
What's a practical takeaway here?
Well, understanding, especially the heap one, it's going to understand better when you generate pressure in the garbage collector. If you, for example, start creating variables and freeing them and creating them and freeing them and creating them and freeing them inside the same kind of size of variables, probably you are not going to need to reclaim more pages because you probably are reusing the same MSPAN and the same pages that you have in memory. So I'm not 100% sure if that is 100% accurate.
Oh.
So, but yeah.
Sounds like if I would want to, like, not hack, but if I want to poke around somebody's code somehow, I'm trying to think if you are playing some capture the flag and you got this piece of program and you try to like poke it to see where will it break. Maybe this is something to try there. Not the most everyday practical use case, but yeah, still trying to link that also into somewhere.
Yeah. It's kind of hard for me because, as I said, I don't find a lot of practical usage for most of the things that I see here. For me, it's about knowledge and about understanding how it works and having better understanding on things like this. It's useful to know when the garbage collector is going to run, probably in very specific real-time applications. You need to know that. But probably if you are doing real-time applications, almost for sure you are not using a garbage collected language. So it's anyway, for that kind of cases, whenever you need to know that, hey, the garbage collector is not going to run in this space, you can say, okay, I can run the garbage collector first, so I reduce the possibility of the timer one to running by itself. And then I can control the size of the heap to be sure that during that time, I'm not doubling the heap. So I don't know if that is something that I will do or I will want. Probably I will try to disable the garbage collector and enable it again later. I don't know if even possible in Go. Anyway.
No, interesting.
Yeah, it's tricky. And yeah, trying to poke around with this. I don't know how you can poke around with this. It's I don't know.
It's lots of arrays until something happens.
Yeah, no, you can for sure you can generate a lot of data and start generating the garbage collector to spin a lot. Actually, you can do things like playing around with the concept of, hey, whenever you double memory, I'm going to generate the garbage collector pass. I can easily double the memory, reduce the memory because I free that thing and double the memory again and free that and double the memory again and free that and double the memory again. And that will generate a lot of garbage collector cycles. But you need to play with that and yeah, you can play with that and screw a bit the performance of the thing because you are doing a lot of garbage collection work instead of real work.
Okay, cool.
And probably you can do even better just reducing the amount of memory needed for the garbage collector phase. You can tune the Go GC to instead of 100, you put that in 10. And every time the 10% is reached or 1% is reached, you run a garbage collection phase, and that's going to be crazy spinning the garbage collector all the time. So not something that I would recommend, but
yeah, very nice segue you gave me here for an unpopular opinion. But before we jump there, could I ask you to recap the 2 episodes on this and just quickly go over all the 10 again as a very quick summary? It was really interesting to hear them all.
Yeah, I can recap of them. One of them was the slices internals. The other one was the Go routine cooperation, the cooperative natures of Go routines. The other one was the concept of the syntax, the abstract syntax tree, and how that sets the boundaries of all the things that can be there in a Go file. The other one was escape analysis plus inlining and how they collaborate to get a better memory usage. The SSA lowering process, that is the process that converts your program representation at that point, the SSA program representation, from machine independent to machine dependent, and how TinyGo leveraged that SSA to use the LLVM technology to generate microcontroller binaries using the exact same Go language, and how the compiler and the runtime collaborate together to provide a lot of the syntax that you see in Go, like sending things to channel or appending things to a map, the entry point of your binary, and how that is not the main function. It's more complex than that. and the memory allocator and how the memory allocator manage your memory and reclaim pages and all that stuff from the operating system. And the final one, when the garbage collector, the GC runs, and what are the 3 places where the garbage collector can run and why. And I think that's it.
Okay. I would love to hear from people who listened to the episodes on this topic, either on Slack channel of the Go Time podcast or on Twitter. What was your mind-blowing one, or what was useful, or what was the biggest aha for you? It is really cool. Go watch all the talks from Jesus. They all will be linked in the show notes. And thank you so much for joining. Do you have an unpopular opinion for today?
Oh, that's hard. It took me some time to realize that I had one. So no, I don't have one for today. I'm going to stick to my mechanical keyboards.
And
Dislike,
mini unpopular opinion is that 2 episodes recorded in 2 consecutive days can share one unpopular opinion.
Yeah.
Great. Then thank you so much for sharing your insights, and good luck in all the cool talks that are coming up for you.
Yeah, thank you. Thank you for having me. And yeah, I had a great time here. So thank you. And I hope, I really want to know more about people getting this knowledge and finding ways of doing that, of using that. Because to be honest, as I said, I'm a web developer. My main focus is on API development. So there's a lot of fields out there that are more system level that probably can take advantage of this kind of knowledge. But for building APIs, everything works so smoothly in Go that you don't really need to go deeper. So it's
do share thoughts, everybody who listened. Yep.
Yeah, let's see what people say. So
all right. Thanks everyone for joining. Thanks, Jesus. Bye-bye.
Thank you. Bye.
That is Go Time for this week. Thanks for listening along. Subscribe now if you haven't already. Head to gotime.fm for all the ways, or simply search for Go Time wherever you get your podcasts. You'll find us. Hey, do you receive our changelog newsletter each Monday? If not, let's fix that bug. One reader calls it so good, he considers it a competitive advantage. Sign up for $0 at changelog.com/news. Thanks once again to our partners at Fly.io, to our mysterious beat freak, Breakmaster Cylinder, and to our friends at Sentry. We love Sentry. You might too. Use code changelog when you're signing up for a team plan and save $100. Why not, right? That is all for now, but we'll talk to you again next time on Go Time.